one of my favorite lines from Geoffrey Hinton is he was giving a video lecture, I think, online, and was saying, we're going to imagine a 14-dimensional space, and we're going to do this like everyone else does it. We're going to imagine a 3-dimensional space and say 14 very loudly. This is kind of how, like, we're like we're trying to imagine something that our brains are really just like not very good at. But there's a sense in which you can begin to get like some like weak intuitions for these spaces, and this is one of the things that I've kind of, I don't know, I'm not going to say that I really deeply get it like I get 3D space, but you can begin to get like little glimmers of what it's like to live in this like slightly higher dimensional space.
How's it going, everyone? The following is a conversation with my friend Lee Sharkey. He works in AI safety research for a company called Goodfire AI. And specifically, he works in mechanistic interpretability, which basically means splitting open AI models and looking inside them to try to understand them better. And I think as AI becomes more important, I really want to learn about what's actually going on inside these models. So I hope you enjoy the conversation. Given that this is basically a brand new field, why did you decide to work in this kind of nascent field?
Yeah. So yeah, it's great to be here. And thanks for having me on. And yeah, so why did I choose to work in a brand new field? Well, there's a sense in which it's brand new, and a sense in which it is a continuation of another field. And I think both of these are very valid perspectives. So where my background is basically in computational neuroscience. Going back further, it's in other stuff, but I came into the field just fresh out of doing some computational neuroscience, and I'd been working in I'd been doing a master's project in a lab that looked at understanding the neural activations of artificial recurrent neural networks, and this basically was used as a model to try to understand biological networks, because these systems are they're arguably very similar in many of the core underlying principles. And so I found that the tools I was using basically, and the concepts and the methods were like very applicable to this area of AI safety. And I ultimately wanted to get into AI safety. That was indeed why I was studying, computational neuroscience, because it was so adjacent to the field of AI, and as I was kind of trying to get into that field. And so it basically, there was this nice intersection between like what I currently knew how to do and where I wanted to go, which was interpretability. So I basically was just like drawn to this field largely because they're very similar to they're basically both just systems of very large numbers of like nonlinear computations. And so but this is both biological and artificial networks. And so like these are just fundamentally fairly similar fields, and I wanted to, do something useful with it.
How do you think that comparison between biological systems and neural networks is really interesting? Because but I was wondering, like, was there kind of a light bulb moment where you were like, okay, I need to focus on AI because this is the most important area? Because I guess a lot of people have been thinking it's such an important area recently, but you may be earlier than other people. What was there like a light bulb moment?
Yeah, there was actually, like, it was in 2014, and I was studying for my undergrad. I was doing neuroscience at the time, just more biological neuroscience, not very much computational stuff. But I was nevertheless reading some, papers in the field surrounding that, and I stumbled upon an old paper by Kwok Lee, and who's the last author was Andrew Ng, and it was basically this paper that it was done. That they were, I think, working at Google at the time, if I recall correctly, and Google had basically combined a lot of computers together for the time, and had basically trained a neural network to uh, like reconstruct images. So there was this like neural network, and there was like an encoder network and a decoder network, and the way they trained this network was basically just like the output should be the same as the input. But the crucial step here was that there was this like little bottleneck layer in the middle, that the encoder fed to and the decoder fed from. And whenever you looked at this little bottleneck layer, there were these like representations that they didn't like train into. They didn't like intend for this neural network to learn anything in particular. They just wanted the input and the output to like be similar. And in the whenever you looked at like the neurons in this like encoder, like output by the encoder, they looked like things, and you could basically like visualize them because you had a decoder there. And so what you could do basically is like activate one of these neurons and see what does this like neuron mean to the decoder. And what you got was you could basically produce like an image of a cat, just from one of these neurons. And just no one coded anything about like cats in particular into this neural network, and yet it was able to just generate an image of a cat. And this was, I think it was a 2012 paper, so I think it was actually slightly before AlexNet, but maybe it was 2011, I can't recall. But it was just striking to me because I was like, wow, there's really like something very similar to a concept of a cat in there. It had really just abstracted all these other things from like all these random images, and just picked out like cat was one of many things. There were other representations in there, but the fact that it could just pick out these concepts was kind of striking, because not really today we've seen neural networks do many amazing things, but and it may not be like that striking to us these days, but back then we didn't really know how to do this very well. And I just remember looking at this image of a very grainy, pixely cat and thinking, wow, deep learning's going somewhere. And it kind of sparked my interest. And I mean, it was a few years after that before I really got into it deeply. This was around the time, 2014 was around the time that I think DeepMind sold to Google. And so like things were picking up, but it was somewhat early in the deep learning revolution. But I really kind of only got into it a little bit later in, say, 2016, 17, 18.
Wow, yeah, there's something kind of intriguing but also terrifying about like the unintentional nature of like discovering that somehow these like representations have like grown in this network in a sort of uncanny way.
Yeah.
But so in your work, which is called, well, the field is called mechanistic interpretability, and correct me here if I'm saying anything wrong, but like I guess you basically spend most of your working time trying to work, like looking very deeply into like kind of the filthy kind of undercarriage of large language models. Um, what are the like tech, or how do you do that? How do you kind of like break the models apart and try to understand them better, and maybe try to, yeah, in a kind of simple way, maybe.
Yeah. So I mentioned that this model had, this old model had learned this representation of a cat, and this is somewhat similar to what other models are doing. There's a similar process going on, and the way neural networks work is that there's these layers, and these layers are just like matrices, which are just big grids of numbers, and they take a list of numbers as an input and then spit out another list of numbers. So these grids of numbers are just used for just taking a list of numbers and putting another list of numbers. And then after that, like there's just a that's called like a linear computation. But then there's like a non-linear computation after it, which is just like, there's you could say something like a threshold function. If it's like above a threshold, then we'd say the neuron is active. If it's not, then it just remains at zero. And so neural networks are just like literally just sequences of linear computations followed by nonlinear computations. And what we want to do basically is whenever we're training a neural network, like these are just like very generic types of transformations, but almost magically, like they kind of learn little algorithms inside. These like two combinations of types of computation can learn like very impressive things if you just train them to do that. And so like I like to call these like neural algorithms basically. Just to be clear, this is distinct from the algorithm that was used to train the network. So there's an algorithm that does the training, and there's an algorithm that it learns. And this like algorithm that it learns is like what is, it's somehow doing like much of these kind of magical things almost that it's doing. And it's these like learned algorithms that are like pulling out the cat representation, but it's also pulling out representations that are much like finer grained. They're maybe not like a full cat, but maybe like a cat ear and a cat nose and a cat mouth. But even finer grained than that, maybe it's just like the corner of a cat's ear, but that also looks like the corner of a piece of paper, or the corner of a tip of a pen. And then there's these other like lower level like representations that it picks up, just like an edge, like say the edge of a paper or the edge of a pen or the edge of a computer and so on. Like all of these are just lower level like representations in some sense. And the way we think about what neural networks are doing is that they're doing these computations that in some sense produce these representations, and these is basically computing over these representations and spitting out something that we have trained it to do. And the way I think about what I do is figuring out what are the like fundamental computations that the network is doing. If we can break up this algorithm into like a set of simplest possible steps that we can understand individually, or at least in relative isolation, then we can basically just try to understand actually what it has learned. Because that's the thing, we don't really understand this neural algorithm that it's learned. Like we didn't code that up ourselves. It is like grown, as you say. And we, we don't get to understand that network for free. We have to do some work to understand what it's like actually learned to do. And that's what I view, what I'm
Yeah, I find it so interesting. Like, is it more work to work out what's going on than to actually, build it in the first place? That's kind of an interesting question.
I mean, well, yeah, currently we know how to train them, but we don't really know how to understand them very well.
Yeah, it's like the power versus understanding trade-off. It's like we've become way more powerful, but has our understanding kind of improved? But yeah, I was gonna say, so because there's obviously the vision models, and then there's the like large language models. But with the large language models, is it like accurate to say that there might be, let's say, like a neuron that fires when a particular concept is used in the input? So like there might be is it accurate to say like there might be like a neuron that fires every time you input Barack Obama into like ChatGPT? Is that accurate?
Yeah, for sure. And I think people have actually found such, maybe not neuron per se, but like a kind of neural activation pattern might be more likely. But there are such representations in certain models, and in fact some work has looked at multimodal models where they can see not only do the I think in the case that I'm thinking of, it was either Barack Obama or Donald Trump, but that they had found neurons for that it responded this particular neural activation pattern or neurons looked at it basically responded to images, both images and like mentions of an individual politician, and so these kind of there's something in there that's computing. This is the Barack Obama. There's something in this text that's about Barack Obama, and this was going to help me predict things about the next words that are coming up.
And so in mechanistic interpretability or mech interp, like, so one thing you'd try to do, like, is to actually try loads of different inputs and see how the neural activations differ based on the input, kind of thing. Is that one thing? Like what are the kind of methods that you use in your day to day to be like trying to inspect, these kind of like computational patterns?
Yeah. So the approach that I think you mentioned is kind of, you show the network a bunch of different inputs and you look at how it responds to these inputs. But there's a crucial step in there, which is like you look at how what responds. Like, are we looking at individual neurons? Are we looking at like individual like neural activation patterns? And I'm going to use like a word like these are kind of, whenever you talk about a pattern of neural activations, you're basically like talking about let's call it a feature, right? So it's like and what we're also going to make a definition here that like this feature is like a vector, like a direction in activation space. This is just a list of numbers basically. A vector is just a list of numbers, and a direction is just like the just another way to think about this. It's like a vector of a certain length. And so when we're talking about neural activation patterns, we might want to say, well, I don't really care about individual neurons, but I do care about the patterns that happen. And unfortunately, like the neurons are given to us for free. We like, this is what we coded into the network. We said this is a neuron, and so on. But whenever we start to talk about activation patterns, well, there's just literally infinite number of like possible different activation patterns that we may like wish to detect. And so, if we were to choose these neural activation patterns or directions in activation space like randomly, well, like there's no guarantee that they'll actually mean anything. There's no guarantee that you will have one that responds to Barack Obama. You might end up with one that seems to respond a little bit to Barack Obama, but also maybe, I don't know, fire trucks and like, I don't know, a can of Coke. Like it doesn't necessarily mean anything coherent. And so what we need is like a way to, if we're looking for these like representations in activation space, you would want a way to like choose these directions, choose these vectors, and this is like what one class of methods does, like sparse dictionary learning. It basically tries to learn activation patterns that like appear time and time again, but they appear like only sparsely, like only rarely in some sense, because not every like sentence that you would give a language model has anything to do with Barack Obama. In fact, most of them won't. And so like the concept of Barack Obama only like happens rarely. In some sense, it's like very sparse in the data set. And so but if you train your this like set of neural activation patterns that you're looking at to be sparsely activating as well, then you may like pick up some of these like more fundamental like representations, so to speak. So this is like one class of methods that people use.
Okay, cool. And I was going to say, because going back to the like neuroscience link, are these methods similar? Because I guess in neuroscience, I guess there are, you could carry out an experiment where you kind of like provide some sort of stimulus to the person and the brain, and then kind of study what happens in the brain. Is there like how sort of similar are these methods, do you think?
Very, and indeed, one of the places that inspired like mech-interp to use these methods was computational neuroscience. In fact, like many of the there's a fairly, I don't know, there's at least a decade or two more even of people using sparse coding methods to try to identify or at least conceptualize things in brains before they were used in neural networks. So yeah, there's a kind of deep similarity there. Now the methods aren't identical. Like there's some implementational details, and but overall, I'd say yeah, there's a pretty like straightforward lineage from one to the other.
Cool. I mean, it's really interesting. And it's like it must be really interesting to be like kind of like right at the start of the field. I was gonna say what like obviously mech interp is really relatively new, I guess, but what are your kind of favorite insights that have kind of come about as a result of mech interp?
Favorite insights. Favorite insights just for me personally, or things that are useful, or
Or just like what are some maybe a better way to put it is like what are some examples of like interesting things that mech interp methods have like found out about neural networks? Because like I think that like that one we were talking about earlier about there's an activation pattern that tends to fire when the input's related to Donald Trump. Like that to me seems really cool. But yeah, I was wondering if there are any other like you know just interesting
yeah,
methods.
like so I mentioned the cat one first of all, and that's easy to replicate. Um, and but there are just many different models, and now we can study models that are just much more capable than they used to be. Um, and yes, you can find representations for all sorts of things. Like somewhat famously, um, Anthropic released a set of like they basically identified many different representations in, I think it was Claude 3 Sonnet, or was it 3.7, I can't recall, but it was basically they found famously like a Golden Gate Bridge feature where it was a piece of it was a neural activation pattern that responded in response to inputs that related to the Golden Gate Bridge, um, also to images of the Golden Gate Bridge. I think if I recall correctly, I could be confabulating at the moment, but it also like weakly activated in response to say San Francisco and so on. But yeah, then there's it's almost the case like what does it not represent? That would be more interesting, honestly. There's just like so much in these models that like if you can think of a representation for it, then it may well be in there. You just need to like know how to look for it. Um, but I think one of the things that I'm like uh, increasingly interested in is just thinking less in terms of say these representations and more in terms of like what are the computations that are generating these representations. And so there's some good examples of that in the literature. Another Anthropic one is say induction heads, where it basically you've got some sequence of inputs, and in the past it said uh, some random sequence followed by then A, B, and whenever later in the sequence you see a character A, well then it should make you more likely to predict B because in the past you've seen this sequence A, B, and so this like induction head basically uh, looks at these patterns in the past and makes you more likely to predict B whenever you've seen A. And this is like a cool generalizable like step in an algorithm that can do ultimately quite a lot of cool stuff. Whenever you're not just um, doing this over say like raw words that you've put on the page, but also over like abstract concepts. If one abstract concept leads to another, then whenever you see this other abstract concept in the future, you should make this it more likely to predict this other abstract concept. And this is like more somewhere where you can imagine something more like how we might think emerge.
That is cool. So I guess you're probably among a small group of people in the world who've spent like a really long time looking like at the kind of like really really deep level and at the models. Like most people who use AI kind of use ChatGPT, which is sort of I guess it provide we look at like the surface we look at like the input and we see the input and the output,
Mm.
and there's that famous meme which is like that monster with the like lipstick on or whatever, where it's like
The shot.
yeah, exactly, yeah. Um, so I guess given that you've like spent a long time like looking at these, I just wanted to ask like on a personal level, how has that felt? Because one reason I was asking this is that I think people talk about like climate scientists as like more deeply understanding climate change because they spent a long time looking at the science, and similarly like geologists understand like deep time. I was just wondering, as someone who's deeply looking at AI models, do you feel like on a personal level you've like stared into some kind of like weird abyss or something? Maybe not weird abyss, but is there anything like on a personal level that you've kind of seen that other people might not have?
Almost certainly. So like, but some of this may be hard for me to access because it's now in my day to day for so long. But I will nonetheless try. Like one of the things that I don't know, I still, in some sense, like neural networks are like really big, and I don't just mean in terms of like number of neurons. Like there's just there's a lot in them, and like an almost unbelievable amount. Like if you look at if you ask um we can kind of view some of this from the surface. We can ask, we can prompt, ChatGPT or anything else, any other large language model with like a question about really a very diverse number of different fields, and it will actually like speak very sensibly on it. And you know, in there's like really how does it do how does it know so much? And one of the things that I think I've like come to appreciate a little bit more is just like how big. One of the ways you can think about um, these like list of numbers that I was mentioning is like fine. They are in one sense they're just a list of numbers, but in some sense they're like we often talk about them as spaces. And by analogy, you have like if I've got a three-dimensional space like we have here, all I need to describe like this point here is like a list of three numbers. Just the height from the floor, the height from the wall, and the height from the other wall. And but so you can kind of and three is like there's much more space in a three-dimensional space than a two-dimensional space. Like you can just there's in fact like an infinite number more 2D spaces in a 3D space. But you start whenever you like this is like a list of three numbers. We can now talk about a list of four numbers and say this is a four-dimensional space. And what this means is very similar to the two-dimensional to three-dimensional case. There's like an infinite number of like three-dimensional spaces in this four-dimensional space. And we're not talking about like four-dimensional spaces in neural networks very often. We're largely talking about like thousands, if not like, tens of thousands of like dimensions. And in fact, I think, in many of these other models, you could begin to start pushing million dimensional spaces. And in fact, there are other ways in which to think about neural networks where a million is very we can also think about the parameters of a neural network as parameters existing in a high dimensional space, and these parameters go up to trillions. And so like you can fit a lot in that space. There's just like a lot of room in there, and I feel like and I'm not going to pretend that I can sit here and imagine a like million dimensional space, or even frankly a four-dimensional space. Like one of my favorite lines from Geoffrey Hinton is he was giving a video lecture I think online and was saying we're going to imagine a 14-dimensional space, and we're going to do this like everyone else does it. We're going to imagine a three-dimensional space and say 14 very loudly. This is kind of how like we're like trying to imagine something that our brains are really just like not very good at. But there's a sense in which you can begin to get like some like weak intuitions for these spaces. And this is one of the things that I've kind of, I don't know, uh, I'm not going to say that I really deeply get it like I get 3D space, but you can begin to get like little glimmers of what it's like to live in this like slightly higher dimensional space.
Wow, that is yeah, that's interesting. It also reminds me of the climate change thing as well, because it's also an issue where it's really hard for people to understand climate change because of like the long time horizon, and it's not kind of tangible. To like it obviously it is tangible to some extent, but also the effects are kind of like really complex and kind of like mediated and indirect and stuff. So yeah, that is really interesting. Do you
I
think like sorry, yeah.
I was also going to maybe add something where it's more just it's a bit more um self-reflective, where it's I I see a lot of like the way I think. I kind of like view a lot of the way I think now in terms of these, in terms of just like ways in which AIs might think. They're like often useful tools to just like think about why did I think about something in that particular way, or why did I, um, you know, why did my thoughts take that particular pattern? And sometimes it feels a bit more intuitive whenever you start thinking about them in terms of just like these similar using similar concepts as you might in mech interp
Yeah,
mechanistic.
interesting. Because I mean, I was listening the other day to Kenneth Stanley, who's talking about the fractured entangled representation hypothesis, which I think his main argument is kind of like the representations are really, yeah, kind of like fractured and messy and stuff. But it's interesting because kind of what we were speaking about earlier with the like our neural networks grown, and do they start to form kind of like geometric structures that are sort of similar to, I don't know, biological organisms is another. Because yeah, I mean, I guess it's an interesting question of like our neural networks. Like, is there something? Are they like quite ugly underneath it all, or or is there some kind of like latent kind of beauty in there? Also, just kind of see as well.
I think both is true, and like this is the same way in which you say might look at an organism and say, is it ugly or is it like beautiful? And in many it depends on your perspective, I guess. Like there's many ways in which just it's very clear that it's kind of ugly, right? So like I don't know, my favorite example of this is the recurrent laryngeal nerve, which is just like this thing that evolved. It goes from our head, so the base of our skull, and like goes the whole way down. I think like through our neck anyway, underneath our aorta, just like in our chest, and then back up to innervate the. I can't recall what it innervates, but it's I think somewhere in the head or neck. So it goes down and goes back up, and this is like bad design, and it's especially bad design because the giraffe also has the same thing. The giraffe's head is like way up there, and its heart is way down there, and this nerve just goes the whole way down its neck to its heart and back up to innervate something in its head or like very high up in its neck or its head. And this is just bad design. It is ugly in some respects, but it's what we've got. But then you look at just like and there's many this is just a particularly obvious and macroscopic instance of this, but there's many such similar um, like fails in micro on a microscopic level. I'm sure they're just like less obvious to us. Um, and this is just because it's organisms are grown, not made. And in a similar sense, um, like neural networks are grown, not made. There's just I don't know. There's a lot of mess in there, but there's also just like an incredible amount of structure. Um, and so in some sense, like yes and no, they are both beautiful and incredibly ugly. But like the beauty kind of emerges from the ugliness.
Yeah. The giraffe thing's interesting. I was listening to, or I was reading something that said, I think I'm right in saying that they drink like really irregularly because it's like quite dangerous to for a giraffe to drink. I don't know if it's related, but yeah, I mean, one other interesting thing is I saw a paper recently which was about the like geometry of embeddings within large language models, and I was sort of saying that there is some sort of like universal structure to organizing information, which is quite interesting because it's kind of like a Platonic sort of, well, maybe not quite, but maybe it's like a kind of idea that there is some kind of universal underlying structure. I don't know, is that something that you think is likely, that there is like humans and LLM structure knowledge in some sort of like universally like kind of equivalent way?
So I don't know about perfect, uh, like perfectly like universal structure, but there's nevertheless a huge amount of shared structure. So like if you look at say you asked about language models. I am less aware of the of studies of those, but say in vision models, whenever you look at like the representational geometry of vision models and say chimp brains, um, it there is like a pretty strong match, and I would eat my hat if there's like not a pretty strong match between say the representational geometry of large language models and those in humans. Now, they large language models will know a lot more stuff, and there will also not be a perfect match. Humans can do things that large language models can't. Large language models can do things that humans can't, and so there's necessarily going to be some like mismatch there. But like I think it's useful to ask like why might they be somewhat similar. Um, and like we can kind of point to this idea of like the Platonic representations, but I think it's like maybe even just more mundane than that. There is a world out there that is giving us information, and this we're basically asking both humans and large language models to take in this information and do stuff with it, and whenever you're like tasked with doing this, assuming you have is nothing has been hard programmed, assuming you're learning everything. Well, the best way to like build representations such that they are like useful is for them to like in a very deep sense reflect the world. Like these like latent variables that you don't have direct access. I have like this mouse here. I don't and in any way, in any meaningful way, have direct access to that mouse. I can see it, but that's just like a 2D projection of like what of the mouse that's actually there. And I can touch it, but like that's just my I have this like arm thing that can go down. There's sensors on the end of my arm, and like there's a sense in which I don't have any like direct access to that mouse, but yet my brain has a visceral feeling that well, there's a mouse there. It's just like there's a latent variable in the world that I do have like uh, you know, representations of. Now, that is not true for every possible thing in the world. There is like this particular cluster of air. Like it is very much a real thing here, but there's like my brain is not particularly interested in representing this cluster. Maybe it's interested in the vague sense that there is air in here, but and often it won't even bother to represent that. And so like there's a sense in which like our brains are picking up like real latent variables in the universe, and because they're like tasked, well, they're learning these things because they're like tasked with doing something with them. In the case of large language models, it's just predicting the future slightly. In the case of our brains, it's probably predicting the future slightly, but also predicting also because it's being asked to do stuff on top of that as well. But yeah, so basically, like there is a there's something out there in the world that our brains are like picking up these latent variables that they're representing. And so, like to the extent that there's a world out there, and to the extent that our brains are doing a similar thing, prediction, as these large language models are doing, we should expect there to be some like shared structure to our representational spaces.
That's great to hear. When you find it out, let me know, because I'm interested to know what the universal structure is. But I think that would be, I mean, that would be definitely a good thing. I think at least to me that seems like a good goal of like using AI to kind of like understand the world better, kind of thing, and yeah, understand like the structure of information. I was just gonna ask, like, going back to your work, because ultimately you're trying to work out what's going on in large language models, and like how far do you think the mechanistic interpretability community has come? Like on a scale of 0 to 100, how much do you think we understand what's going on in a large language model?
It's very hard to give such a number. However, it's probably in the lower half at very least, if not lower. Maybe there's some sense in which we understand quite a lot, but maybe there's some sense in which we understand almost nothing. Um, do we understand the kind of things that it may be computing? Well, like we've got some sense of that. We can like look at these neural activation patterns and we can see, well, it does seem to be like responding at least to this picture of a cat, this Barack Obama. It seems to have a concept of Barack Obama. And so there's like a sense in which we know, well, it's somehow computing, it's somehow like separating out things that relate to Barack Obama or cats or whatever, and it's doing so. Its computations do result in these things. We don't really have a great sense of like the step-by-step process by which it builds these representations, and so in that sense, we like understand very little. We've got some insights, but I would suspect that I don't know. It's hard to give a number, but if you really force me with no error bars, 1%.
Wow. And where can we get to with mechanistic interpretability? And the reason I ask this question is I think that I'm right in saying that so Dario Amodei wrote the CEO of Anthropic, he wrote an article I think in a few months ago saying like mechanistic interpretability is super important for us to like validate whether AI is safe. Don't quote me. I think it was along those sorts of lines. Then I think Neil Nanda wrote an article kind of saying mechanistic interpretability might not be able to like validate that an AI model is safe. So yeah, I mean, I guess my question is how far can mechanistic interpretability get?
So yeah, I'm aware of that. Those two sources, and I think what might be explaining the difference is, and I haven't chatted with like Neil on like why he kind of thinks that in particular, but if I'm to try to simulate Neil, now this is to be clear, I simulated Neil, not Neil himself, and so he can hopefully correct me at some point. But my best guess for like why they might be saying these things differently is that like one might be talking about current methods, and another might be talking about ideal future methods. And I think many sensible people would agree with both of these things. Then current methods are like I would not want us to rely on them to make systems that are vastly smarter than humans safe. But at the same time, I do have a great deal of hope for what it might eventually be able to achieve. If we can just build better methods, apply them at scale, and really analyze the results of these methods, and basically build up like whether it's in our brains or whether it's in other AI systems, build up good understanding of what's actually going on in a given AI model. And yeah, I do think it's important to be able to say verify other methods. We may think that we are making models safe by using a particular training method or by monitoring chain of thought. And like there may be good, like some good reason to think that, but like wouldn't it be nice if we could like actually verify that rather than just have kind of correlational or kind of good reason to believe it just because of optimization. We might really want to just like look at the steps that it is using to compute its output and say, well, okay, this was actually a safe series of steps, and there's no funny business going on in between, because like we know funny business can go on in between and like does in practice today, and whenever and like that that causes basically the problems that it causes today are like not as serious as the problems that it might cause in future when we're dealing with much more intelligent systems and having given them much more responsibility in our lives.
Interesting. Um, because I guess I was gonna ask also because a lot of mechanistic interpretability takes place within the major AI labs, right? Like OpenAI and DeepMind. Obviously, not all of it though. But I was wondering, like, what do you think the field should look like? Like, do you think, for example, government should be like pouring way more money into mechanistic interpretability? Do you think it's right that the research takes place within the labs? Like, does that make sense, do you think, or should more of the research be done like outside the major labs?
Um, so I'd say these days that like probably a minority of the research is being done in the large labs. Now that was not always the case, and quite recently it was the case that like a pretty vast majority of it was. Well, I don't know how much to stand by that statement, but a much larger fraction of it was being done in labs. Um, and but like increasingly more people are interested in doing it. The UK government, for instance, is doing some work on interpretability inside the UK AI Security Institute. Um, and there are other companies that aren't scaling labs, such as the one I work at, Goodfire, that which are doing mech interp, but are not one of the large AI companies. Um, and there's an increasing number of academics and independent researchers as well. How do I think it should look? Well, yeah, I do think that I think a lot more people should be interested in this field. I think like it's really been surprising to me, um, how few neuroscientists have just like jumped ship over the years. Now there have been a non-zero and substantial number that have. However, one of these things feels like way more pressing, AI in particular, and is just a much like easier system to deal with, and has yielded in the short period of time that it's really been, a field, has yielded like I would argue like a lot more progress than in the in the field of neuroscience, just because it's just very hard to make progress in neuroscience. It's just a very difficult object to deal with, the brain. If you try to the way you might record from a neuron is if you poke it with an electrode, which is just like a ultimately like a sharp needle that is able to read things, and that, it turns out, damages brains. For instance, this is just one of the like many problems that you would have whenever you're trying to do neuroscience. But none of these problems really exist in mech interp, and it feels just like a really interesting system for neuroscientists to jump on and like start uh, doing their field, but on another object. Now, like I don't want to that won't be for every neuroscientist. There's just like so much more in neuroscience than what goes on in the particular branches of computational neuroscience that might be interested in mech interp. But it nevertheless surprises me that like so much of like mech interp is still such a small field, and is nonetheless very pressing a very pressing set of questions.
What? Because I mean, I was just wondering whether like people who use AI, whether that's kind of like large organizations or individuals, should be, should say like, hey, what's going on in this model, OpenAI? I don't know, like, should there be more sort of that type of thing going on, or do you anticipate that's something that could happen? Or...
I think I do anticipate that as something that could happen, but right now OpenAI and other companies have a very easy answer, which is, well, we don't really know, and no one really does. Like we can get some insights, like we can. I do think that these like larger companies could make more effort to understand, like using the tools that we do have, what you know, get whatever insights we currently can out of these models, but in some sense, like the kind of thing that people are asking about, like whenever they ask like what's going on inside, might not be so easy to get from these models, and just because the science may not be there, I don't want to give AI companies like too much wiggle room here. I do think that they could be doing more to actually give insights about what's going on inside, and I do think people would benefit from that. But I think often like people want something different than might be possible. However, not always.
Interesting. What is your ideal outcome for AI? Like, let's say 10 years from now. So what's your ideal outcome, and what do you think is most likely to happen over the next? And also, you can change the time period if you don't think 10 years is a good time period. But yeah, like what's your ideal outcome, and what is most likely to happen, in your opinion?
So the ideal outcome is there's really like a very high upper bound for how good it could be. It could be as much as suppose like AI goes much quicker and much better than we might think it currently might. It may really just solve many material and even non-material issues that we have today. Many of the problems that we have today are just problems that we can solve by more intelligent action. This includes, solving disease as a problem, but then also just like making us more fulfilled and like, I don't know, better humans. This is ultimately a problem that do we think there is some extent to which the action of, say, therapists is like intelligent behavior? Well, of course. And so like we expect that like through intelligent action we can make individuals and society better? Then yeah, we definitely can. There's a lot of thorny questions about how to manage this on a societal level, but it really the upper bound for how good things could be is like, I don't want to say unlimited because it's only 10 years, but it's like it could go very quickly. It could go very well very quickly. How do I think it's ultimately going to go? I don't know. I think it will be like something of a mixture, probably. Some parts might go quite well, some parts might go very poorly. I have just so much uncertainty about like how well things are likely to go. In some respects, things are going like reasonably well, in that like we have systems that are pretty smart. They're pretty steerable. On the other hand, these systems are not like much smarter than humans yet, and are already beginning to show signs of like it's difficult to get like steer them to do exactly as we want. It's difficult to steer them to like not sometimes actively deceive users, or indeed the people that are training them. And that's just one kind of, this is just like on a technical level what might the problems be, which can also just not to downplay the point, but that could also be extremely bad from as they become very intelligent, and we hand over much more responsibility to them. But then I think a really important source of downstream issues may be just, even if things go well in that regard, like how are we going to coordinate as a society to actually make this go well? There's things can, if you fundamentally believe that all humans are good, and doing the best by their lights, we still end up with like very some aspects of the world that are very suboptimal, and you might attribute these to coordination failures, communication costs, and so on. Like if we could just get rid of coordination failures and communication costs, well then maybe things would actually be a lot better even. But we just can't. They're a fact of life. And so like the fact is that even if things go well with individual AI systems, we need to think carefully about how these, like the effects that they have when they interact with us, when they interact with each other, and society more broadly.